So thanks for joining. We've got Graeme Sait here today. This is our second series of Cropping Convos, which are casual Q&A sessions where you can ask your burning questions to leading specialists in the regen cropping space. And we've also got a few more speakers this week, including Jade Caloran, Joel Williams, David Bushell, and Beck Hammersley next week. So check out our website for more info. And just a little bit about Soils for Life before we get started. Our mission is all about supporting Australian farmers to regenerate soils for resilient businesses, landscapes, and communities. And so this Cropping Convo series is part of that, trying to support grain growers in making that transition to a more regenerative practice. And it's part of our Cropping Resilience project, which is all about supporting grain growers to build soil health and drought resilience, funded through the Australian Government's Future Drought Fund. A bit of housekeeping before we jump into it. If you can stay on mute, that would be really helpful. Please ask any questions in the chat. Graeme's going to present for 10 to 15 minutes, and then we can go straight into questions. If it's an in-depth question, we can pull you off mute and you can have a chat. Otherwise, if it's just quite a straightforward question, we can stay on mute. We're going to try and keep to time. It's 7 p.m. where I am anyway, and where Graeme is. So please forgive us in advance if we have to cut tonight short. We're recording the conversation as well. So hopefully it's useful to everyone. Sorry, I've just jumped ahead. I'll hand it over to Graeme now. Graeme, I'm sure you're all very familiar with, co-founder of Nutri-Tech Solutions, and we're very grateful to have him here today. He has a wealth of knowledge around plant health and soil health. So thanks for joining us, Graeme, on a Tuesday night. I'll hand it over to you.
Pleasure. Yeah, so I started Nutri-Tech after a life-changing event with a daughter who was almost killed, and when she was in a coma, it was sort of a thing that triggered my formation of the company. And it's 30 years in, and we're in 55 countries, and when I couldn't travel and teach, which is my major love, is spreading the word, I set up a podcast, and the podcast is I didn't really anticipate how popular it could become, and so I think it's in 72 countries and 400,000 listeners now. So puts a lot of pressure on, though, because there's a lot of expectation. But anyway, we'll that's called the Nutrition Farming Podcast, if you've not heard it. But for me to talk for 10 minutes is very, very difficult, so I better just keep on target. If you've ever heard me speak before, they call it drinking from the fire hose, because there's a lot of information in a short time. Okay, we'll have the next slide. Thanks. So we're going to talk about what basically it used to be called biological farming, this sort of middle ground thing, this regenerative approach. And then at one point we had some dairy farmers who wanted to brand their milk, real milk, from biological dairy farming. And basically when they've hired a marketing company to look at that name, most of the correspondents who they asked said when they heard the word biological farming, they thought of guys in white coats tinkering with genes. Or they thought of biological warfare. It actually wasn't a good name in terms of consumers, and we'd used it for decades at that point. So that's when regenerative sort of surfaced. And because of my focus on nutrition, and when I talk about nutrition, I talk about minerals, microbes, and humus, and the interplay between those, I refer to the term nutrition farming because it's sort of what it's all about. So it's an integrated, holistic system where we recognise that everything's interrelated. Soil health, crop resilience, animal vitality, farmers' health is just as important. So I have quite a focus on your health and nutrition and longevity and how you can live a kind of longer, happier life. But the major focus, and I'm a farmer myself, I've got 2 farms, the major focus is profitability, because you can be as idealistic as you like. you've got to make money to indulge your passion. So it's constantly a story of how we can be more profitable. Okay, I'll have the next slide. Thanks. So as I mentioned, this interplay between minerals, microorganisms, and humus. So when we talk the mineral side of that equation, we look at soil tests, and we like to measure, a whole spectrum of minerals on the soil test, including things that aren't commonly measured, like cobalt and molybdenum, for example, even if you just do it once to find out where you're at. And we also like to see total minerals, even just once every now and then, so we can look at the reserves to understand what's there, particularly when we're using biology to access things like phosphorus and so forth that are locked up, and phosphorus tends to do that very quickly. With our soil tests, I've identified a series of key ratios. The most important of those ratios is the calcium to magnesium ratio. And the reason for that, as I often say, is that when you're growing, you're managing two things. It seems simple, but of course it's not. And those two things are that you're managing gas exchange. You're managing how freely does your soil allow the diffusion. Diffusion is gas moves from a high concentration to a low concentration, so you've got an atmosphere full of oxygen. And when we talk about oxygen, we talk about the single most important element for all carbon-based life forms. It's the most important element for plant growth. And so the oxygen diffuses into the soil if the soil is friable, it's got some crumb structure and so forth. And then the organisms around the roots themselves utilize oxygen. They breathe out, and CO2 now diffuses out. The little pores on the underside of the leaf capture that, combine it with water and sunlight, and that's how you grow stuff. So the better you can manage gas exchange, oxygen and CO2 out, the better you do. And the central physical link to managing gas exchange is the cal-mag ratio. Calcium is this large ball of an ion, the largest ion, two positive charges, grabs hold of clay on either side with its two charges, clay is negatively charged, pushes apart the clay, opens the soil, it's called flocculation, and magnesium's the opposite. Magnesium's two charges as well, but a tiny little golf ball that grabs hold of clay and pulls it in tight. So it's all about, you say, I'll forget the magnesium, I'll just do the liming, but you can't forget magnesium because that's your second role. Your second major role is that you're managing the green pigment called chlorophyll that houses the little sugar factories called chloroplasts. And the chemistry of chlorophyll is magnesium in the center with 4 nitrogens tagged onto the magnesium. So you can have all the urea in the world, but if you haven't got magnesium there for it to tag onto, you're banging your head against a wall. So magnesium is huge. You can't say forget magnesium. It's about a ratio that varies between the amount of clay you've got on your soil is what's appropriate for that cal-mag ratio. It could be 3-to-1 in a sandy soil. You want more magnesium. And a sandy soil to give structure to a soil that has none, and it might be as high as 7-to-1 in a heavy clay soil, and you're going to be somewhere in between that 3-to-1 and 7-to-1. And there's an ideal for every soil type, and there's some of the key ratios there on the slide. And you can see the cal-mag ratio rightly at number 1. We look at other things. We look at the phosphorus to sulfur ratio. We look to see equal parts per million of phosphorus and sulfur. Phosphorus shuts down sulfur, sulfur shuts down phosphorus. They're most available at 1-to-1. Sulfur is deficient everywhere we look. It's a leachable anion. We used to get it for free in the rain. We don't anymore, of course. We banned sulfur emissions. Humus is the only thing that holds it. We lost 2/3 of our humus. So sulfur is a major issue in most soils that we look at, but we like to sort of line it with phosphorus and sulfur. I won't go into the other ratios at this point because I've only got 10 minutes. So we'll go to the next slide. And we'll just sort of talk through. These are tag-ons that just sometimes you want to include on your soil test, and they're not typically included. We measure silica on a soil test. It's kind of the flavor of the month. If you want disease resilience, if you want cell strength, silica is what governs cell strength. And there's this whole recognition. There have been 9 international silica conferences in the last 10 years relative to the potential for this mineral, this neglected mineral in agriculture. Chloride is a vegetative mineral. If you live near the coast, you'll never be short of it because it's evaporated as sodium chloride and dropped on your land within 100 k's from the coast. But if you're further inland than that, chloride's vegetative, and you're not going to have vegetative oomph in the absence, so you do need to test for it. Molybdenum is lacking in 80% of the soils we check, and it's huge. You've got 74,000 tons of nitrogen above every hectare as gas in the atmosphere, and you're supposed to get some of that free gift. And that comes from nitrogen-fixing organisms making an enzyme called nitrogenase that grabs the gas and turns it into ammonium nitrogen. That enzyme is made from molybdenum. If you don't have your 0.5 of a part per million, you don't get the free stuff. So you buy more and more from the bag. So really important. Cobalt, not as important, but pretty important because cobalt is often referred to as mother's milk for those same nitrogen fixers. And selenium, of course, new recognition that it's playing a role particularly in plant immunity, just like it does in animal and human immunity. Okay, we'll have the next slide. Thank you. So that's just one of the things we sort of drive home is that no mineral's an island. Every mineral affects another mineral. And in some cases, like calcium affects 7 minerals. And that's why we look at calcium if we can afford to in various scenarios. Sometimes it's just in the root zone, but calcium directly impacts the uptake of 7 other minerals. And if you do too much, and this is what the balance thing's about, it's kind of the Goldilocks mineral that you have to get right. But if you overdo it, if you had the luxury of doing that in broadacre, often you don't, then calcium shuts down the same 7 things that it otherwise stimulates. So it's hugely important to get calcium right, but all minerals affect each other positively or negatively. And that simple little chart that most of our growers keep on their wall helps you understand your soil test and your soil test relative to a tissue test, because the soil test doesn't match a tissue test. There's often very, very different readings on what the plant's actually accessing, and that's relative to you've got too much of one thing shutting down another, or too little of another not stimulating the uptake of another, and so forth. So that little chart can help on that front. No, next slide. One of the things, and I mentioned leaf testing, even if you just do one leaf test, I consider it so important, but even if you just do one leaf test prior to flowering, that's the business end of the season, and it really makes a huge difference. What we often find, for example, is that you're boron deficient at that point, and a foliar spray of boron can be so productive because it governs the filling of grain, the filling of the head, amongst many other things that boron does. But I consider it driving down the highway with a blindfold on if you don't do one tissue test during the season. And what we've discovered, and it's a handy little tool, it was actually Gary Zimmer who discovered it, but we've sort of extended the understanding of it, that in that leaf test where they give you guidelines for each mineral, if you can get 4 of those minerals at the luxury end of the range, so that might say 0.64 to 0.6 for calcium, well, you want 0.6. It might say 3 to 17 for boron, well, you want 17. That's a luxury level. And the minerals are a surprise. They're not, calcium obviously is not, because it's often called the trucker of all minerals. Magnesium, the centerpiece of chlorophyll, obviously needs to be there. Phosphorus, you can't make sugar without it. All the enzymes involved in photosynthesis are phosphate-based, including the starting point, which is adenosine triphosphate, the battery of that whole process. So huge. But then you think surely the 4th of what we call the big 4 would be nitrogen or perhaps potassium, but it's not. Surprisingly, it's boron. And so it sort of drives home the importance of this little trace mineral. And part of it's because of the huge importance of calcium, and calcium doesn't work without boron. Calcium, the trucker of all minerals, and boron, the steering wheel. So, and what we find is that in leaf testing across the globe, in many, many countries in which we work with teams of agronomists, 30% of the leaf tests, not only are those big 4 not in the luxury range, they're all in the deficient range, and you're not having fun farming. If you've got the 4 most important minerals for the most important process, all deficient, you're not going to enjoy your farming career. And that's 3 out of 10 farmers. And so I take it as part of my role to change that and make people aware that, you know, you can monitor and you can change these things and reduce your stress load. Okay, we'll do the next one. So that's what 3 out of 10 leaf tests look like, where those 4 minerals, phosphorus, calcium, magnesium, and boron, are all deficient. And as I said, you are stressed at that point. Now, the problem with addressing that is that this is more likely to be in a more intensive horticulture than broadacre, but very commonly in, say, vegetable production or for orchard production, you'll find that nitrogen, for example, is excessive. So how do you address calcium? Because you've only got calcium nitrate. Or you might find sulfur is excessive because people overuse the sulfates in those scenarios with fertigation and so forth. And basically, what have you got for magnesium? Well, you've got magnesium sulfate or magnesium nitrate. So we had to look at other ways, and that's where we come up with the idea of micronizing minerals. And it's become really, really popular, but even in broadacre, to put in liquid inject or use small amounts of micronized minerals right in the root zone is just a instant direct kind of uptake of those minerals. So to pull it right down to 5 microns, and we utilize those minerals in that size, and then we can play the big 4 game. We can put just calcium. You can get 1.1 kilos into 1 litre of lime. It's 44% calcium, whereas calcium nitrate's 18%. So now you can foliar or liquid inject that material and just address calcium and no unwanted tag-ons. Okay, we'll go to the next one. So that's sort of roughly the sort of mineral story, very, very brief brush over. But the microbial story, we're talking about really what's more important, minerals or microbes. Well, increasingly it's starting to be recognised perhaps that the microbes in that chicken and egg game really are the more important, the most important, particularly with findings like rhizophagy, this discovery in the last 5 years that plants are actually eating microbes, pouring out a superoxide, stripping off their outer wall and gobbling up their insides, and 50% of their entire food comes from that. And then they spit out some of these microbes without a cell wall, and these blokes rebuild their cell wall, communicate with the other microbes, crowd around that root waiting for their daily feed and say, look, I've been inside, this is what this bloke needs. And so then they then deliver the requirements of that plant. So that's through quorum sensing communication. And it's just like, who would have thought? And you start to realize just how important the soil life is in the equation. So part of what we call microbe management is that your paradigm shift is that you're dealing with a living system, and everything you do impacts that. So you try and make your practices microbe friendly. And so that obviously involves reducing soil disturbance, particularly when we're talking about things like beneficial fungi, which are hugely important in the equation. We don't want to slice and dice them. So we can see that things like no-till or minimum till can be much more productive. Buffering your salt fertilizers, buffering your acid fertilizers that have been proven to be quite harsh on things like mycorrhizal fungi. DAP, when it breaks apart, the phosphoric acid sizzles up mycorrhizal fungi. And so there's ways that you can make that softer, and you can buffer, put some humic acid with your DAP and things like that. Introducing new microorganisms, huge. That diversity, if we look at the definition of science, adherence to natural laws and principles. Well, what's the central principle of nature? It's biodiversity, that nature likes the more the merrier. And so compost gives us our opportunity to replace some of that microbe diversity, or a huge amount of that microbe diversity. And of course, there are also a variety of task-specific and broad spectrum microbial inoculants, many of which you can brew up on farm to bring more of that diversity. And they can be quite specific. They can be nitrogen fixers or phosphate solubilizers that you can brew up inexpensively and release those locked up minerals. Okay, we'll go on to the next slide. So part of that mastery of the all-important microbial equation is this understanding of cover crops. And now that we have a little tool called a microbiometer, for example, that measures increases in microbial biomass, what works and what doesn't, we find that these cocktail cover crops are of tremendous value. I'll just go to the next slide, sorry. The cocktail, yeah, back one. Yeah, that's it. So, because we're just working our way through those points. So the cover crops, you've got that diversity of plants all feeding different, understand plants don't just feed glucose, they lace the glucose with whatever they need. If they need someone to deliver manganese, they feed manganese reducing organisms. So the greater diversity above ground, the greater the diversity below ground, the greater the resilience, the better the productivity and so forth. So cover cropping, cocktail cover crops are of tremendous value. Stimulating and creating better soil conditions with humic and fulvic acid. Foliar fertilizing, which was never a thing in broadacre, is now a huge thing globally. I work in Saskatchewan on a huge scale, and so many of the growers have basically tossed out their fungicide rigs and converted them to precision nutrition via foliar fertilizing. Do a leaf test, give the plant exactly what it needs, and reap the benefits. Trying to eliminate or soften the more damaging chemicals, and of course trying to bring back our earthworms as part of that mastering microbe story. I'll go to the next slide, thanks. So I mentioned that just briefly, that's a microbiometer, which is a simple little tool, just under $300, that measures two things. It measures the microbial biomass, and secondly, it measures the fungi to bacteria ratio. Now, we talked about that all-important gas exchange that you're managing, how freely does oxygen come in, how freely does CO2 emit from the soil for photosynthesis. The physical link, the mineral link was the Cal-Mag ratio. The biological link is the fungi to bacteria ratio. Fungi create the larger aggregates. They create that soil that can breathe, and they're absolutely decimated in most soils that you look at. So it becomes a challenge on how can we resurrect that fungal component. So very, very, and what we find with that tool is it's a great paradigm shift, because you can walk onto any farm almost and say, okay, show me your best paddock, show me your worst. And the guy's looking over your shoulder, he's never thought about microbes in the equation in some instances. And he watches that test unfold, and the good paddock measures 700, and the bad paddock measures 120. And suddenly it's like a penny drop in, oh my goodness, the microbes are making me the money, which is very often the case. So that's a handy little tool called a microbiometer. Okay, I'll go on to the next one. Racing along here. So that became in biodiversity. One of the findings that I think is Nobel Prize winning is from a Brazilian agronomist who'd be great to have a chat with you guys. I'm sure he would. He's very accommodating. His name is Dr. Adamir Caligari, worked for many, many years just on cover crops, but he discovered the concept of putting 5 different species within a blend and the importance of doing that. So the 5 species are grasses, brassicas, cereals, legumes, and very importantly, just 1% of the blend, chenopods or chenopods, it's actually pronounced, which is just a small group of plants that includes everything from the beet family, amaranth, quinoa, and spinach. But that 1%, if it's not there, what's been discovered by the USDA saying, well, why is it you're getting this 4 cover crop response in 1 cover crop cycle? How the hell is that possible? They discovered that only when the 5 plants are present, the plants begin messaging each other and pouring out into the soil very strongly measurable quantities of substances called phenolic compounds. And just as they are the most powerful antioxidants that affect each of our cells, it appears that they put soil life into hyperdrive, and that's the explanation for the 5 species and how that works. We'll move on to the next slide now. So finally, the critical importance of humus in the equation. Minerals, microbes, and humus. We're talking about this storage medium, the only thing in the soil that can hold everything. Clay holds positively charged minerals. Humus also can hold positively, but it's the only thing that stores very leachable, negatively charged minerals, anions, things like sulfur. Humus is the sulfur storehouse. Humus is the boron storehouse. Humus is the nitrate nitrogen storehouse, and so forth. So hugely important from that perspective, but also the home base for the microbes that made it, their support system. And of course, when we look at mineral delivery, we find that there's a microbe behind every mineral. There are nitrogen fixers, there are phosphate solubilizers, there are iron reducers, manganese reducers, potassium solubilizers. There's literally, and that's what the plants are doing. When they feed the organisms beneath their roots, they're saying, well, I need a bit more iron or whatever. And so I feed iron reducing organisms who deliver my requirements. So I lace my sugars with whatever I need at the time, which is quite interesting. Go to the next slide now. So when we talk about proactive pest and disease management, it's been quite a discovery, this recognition of the role of silica. When we talk about, okay, how can we reduce the need for fungicides and insecticides, the starting point is just, okay, you've got a cell wall that the insect's got to bite through. It's quite a substantial wall, and the fungi's got to drill through that, the disease organism, to get to the yolk in the center of the cell, which is the food source. Both the insect and the fungal disease are chasing that cytoplasm, the yolk in the center, and then they can subdivide, and you'll get downy mildew spreading across your plant or something once it's got a food source. So the obvious proactive strategy: how do I strengthen that cell wall? How do I buckle the hyphae? How do I wear the mandibles off the sapsuckers? And that's the story of calcium and silica, and it's become huge. And I use it on my farms. So many people have recognized the potential. And now, of course, the big discovery at the most recent of the silica conferences, this huge discovery, that silica is an immune elicitor, and not just an immune elicitor, potentially the most important single immune elicitor. And when we measure silica in the plant available form on a soil test, you need 100 parts per million. Most conventional growers have got 10, 15, 20, 25, quarter of what they need of that protective mineral. Organic growers have got double. They're still, most of them don't get the 100 parts per million, but it does suggest that there's something, and we don't know which of the chemicals, or whether it's a group of them, that's affecting the organisms that make silica available. So then we look at how we can change that. So I'll just turn that off.
Feel free to start dropping any questions or topics for discussion in the chat, everyone. Thank you, Cole, for the question.
Yeah, start chatting now if you like.
Cole Freeman Hunter from Local Land Services has asked about the microbiometer. It uses a very small amount of soil. Do you have a method or protocol for soil sampling with the microbiometer?
Yes, it's the most important thing is that you're taking soil directly off the roots of the plant you're testing. And it's very interesting to see, just to quantify things for yourself. If you take the soil off a legume, like a clover in a pasture, for example, or a legume within a cover crop, and then you take it, say, off ryegrass, the difference is quite, and it really drives home the role of legumes, because the fungal levels are always much, much higher in that soil that wraps around the legume root. And that's because the legume is pouring out an acid exudate that stimulates fungi. So fungi proliferate in that scenario. But the question is that legume functioning? And over half of the fields that I walk, not just here, but globally, those legumes are not functioning. They either don't have nodules, which means none of that can happen, or the nodules don't have this red pigment called leg hemoglobin present. And if you don't have leg hemoglobin, you're not fixing nitrogen. If you're not fixing nitrogen, you're not releasing the acid that also solubilizes phosphorus and calcium, which tie together, and this acid releases them. So you're giving phosphorus and calcium and nitrogen to the neighboring crop, but you don't get the fungal stimulation because that acid exudate is the byproduct of that whole nitrogen fixation process. So it's really important to get on your knees and have a look. Have you got nodules? If you haven't, that's usually sulfur. And are those nodules red inside or reddish pigment inside? And if they're not, that's usually molybdenum, and that's the missing mineral, and you need to get a little bit of molybdenum into the equation to fix that. So basically we take that little bit of soil. There's a whole sort of a certain amount of water that you put into a little test tube. You take a very precise amount of soil with a syringe that you compress up to as hard as you can push on the end of your finger with a syringe. It's not a syringe with a needle, it's just an empty syringe. You put half a gram of soil into that water, and then you stir it with a little stirring machine that comes with the kit. And then you wait for 20 minutes while basically the chemical concoction and the powder that you've dissolved previously into that test tube. So sorry, I missed the link where you put the powder, a little sachet of powder into the test tube, then you put your soil, then you stir it all, and then you wait. And basically the powder envelops the microbes that have been dislodged by the stirrer. And then you activate your phone, and you access the microbiometer app. And the phone then the app activates your camera and a light the light that you might use to find your car keys or your door, the keyhole sort of thing. And the light refracts off the encapsulated microbes, and there's a little program in that analyzes what the microbial biomass was. It's pretty clever, and I mean, it might not be as accurate. It's not telling you exactly what microbes, but what we find is the higher the reading, the better the paddock, and there is no exceptions. The worst paddock will have the lowest reading. So it's got some tremendous value in that context.
Cole feel free to come off mute, Cole. He's asked, are you saying that you dig up a root and take soil sample from there, or more generally from the root zone?
Yeah, from right off the actual roots. You pull the plant out and you shake the soil onto a saucer, and sometimes you put it. You don't want to have little bits of gravel or anything in there, so there's a little sieve that comes with it that you run it through. You're only chasing 1 gram of soil directly off the roots. So basically, you're measuring the best there is. The difference between the number of organisms on the root versus 6 inches on a bare patch of paddock is phenomenal. I mean, all the organisms are hanging around the plant root waiting for their feed of sugar. So that's where all the action is. And if you want to sort of get across a reference of what's happening in the soil, the best place is right beside that root, right? You pull the soil actually off the root, and it's going to be your highest reading, of course, but it gives you a good indication of where you're at and what's there, because whatever's there is going to be beside that root, enjoying that daily feed.
Thank you. Thanks, Cole. James has asked maybe quite a large question. I'm not sure. He's listened to your podcast on foliar feeding a while back. Is it possible for you to give some guidelines on brewing your own bioferts, and how and when is best to use them, also in what quantities?
Okay, so well, there's some simple little guidelines. If you're going to do, in broadacre, it's obviously much more cost effective to make your own fertilizers based perhaps on a leaf test or a soil test, and if you recognize what you need. So the simple rules of thumb say that we're talking trace minerals, which we'll talk first. Basically, all of them except for copper are 1 kilo per hectare as a foliar. So if you're zinc deficient, which is very common in broadacre, then 1 kilo of zinc sulfate. And then the trick is that you collate it yourself. I mean, you can buy zinc chelate, which is a much more effective way of getting things into a plant, or you can collate it yourself. And the most effective by far, there's nothing comes really close to it, is fulvic acid. So you can use fulvic acid powder with zinc sulfate, and that creates a zinc fulvate on contact. And now you've got and fulvic acid, of course, has multiple benefits in its own right, but what you're doing is collating the zinc to get better uptake. So you're usually using amounts like 200 to 300 grams, say, with a kilo of zinc, 200 to 300 grams of soluble fulvic acid powder with the zinc. And that 1 kilo rule applies to everything. Boron is almost always needed before flowering. We do so much leaf testing globally, and we want luxury levels, and no one's got luxury. So almost everything, I mean, there's very rarely, and I'm talking 0.001% of the time, you might have a boron toxicity or something. It can happen, but it's so rare. So it's a safe bet, even without a leaf test, to assume that you're going to get a significant benefit from a foliar spray boron before flowering. And so and that's the 1 kilo. So 1 kilo of sodium borate, it's often called soluble in the shops. 1 kilo of sodium borate before flowering, that's the timing. Zinc will be earlier on because the role of zinc, you're going to do that in the early vegetative stage, because we're talking about a mineral that does many things, including often called the drought resistance mineral, because it gives plants better access to moisture. But most importantly for zinc is the fact that the hormone called auxins that plants produce is zinc dependent, and auxins govern leaf size. So a zinc deficiency will mean a smaller solar panel and less productivity, not sometimes always. Your zinc deficiency is going to cost you more than any other trace mineral deficiency, because you're going to have less productivity when you've got a smaller solar panel driving everything. So zinc becomes really important. And as we said, just a kilo of zinc, it becomes quite inexpensive in that context. But if you've done a tissue test, you're not guessing. You're saying, okay, I need some zinc, I need some manganese. So again, manganese sulfate at 1 kilo per hectare, zinc sulfate, iron sulfate, copper sulfate. The second thing that we always sort of teach how to do, we teach you how to brew your own on-farm organisms. We call them BAM. There's also a product called EM, which is similar. And they're very simple and very inexpensive, and they're really user-friendly, because they'll sit there for 2 years in your paddock, and you can use them whenever you want if you brew up 1,000 litres or whatever scale you are. It might be a bigger tank than that. But what we use with the microbes is this concept of putting the microbes behind the minerals. So when we do, and of course, there's a whole bunch of reasons for that. The microbes are doing things in their own right, but they're also increasing mineral uptake. They increase stomatal opening when they release CO2, because the stomate responds to a sudden increase in release of CO2. And so you get this better mineral uptake when you put microbes with it. So if you've made something that's costing you 30 cents a litre, and you put a couple of litres of that with your foliar spray of zinc sulfate, for example, well, you put it with everything. There's nothing on my farms that doesn't have the microbes behind the minerals. But the one caution, and there's traps for young players everywhere in this practice, is that you don't put copper. You can't put copper with microbes. Even 100 grams will kill the microbes, and we've done the work to show it. Copper is absolutely toxic, biotoxic. It's a biocide, and people say, oh, yeah, it kills fungus. That's what we use as a fungus. Well, it kills everything, not just fungus. It kills protozoa, it kills bacteria. It's really harsh, and you can't put it into a tank with microbes in it and hope there's some microbes left. So that's just a little rule of thumb with that one.
Thank you. James, let me know if you have any follow-up questions.
So I just continuing. So that was trace minerals. If you were magnesium deficiency, well, we're talking in broadacre scenarios, you would use, again, fulvic acid to collate and magnify, and you would use amounts like 3 to 4 kilos of magnesium sulfate, which is only 50 cents a kilo, so that's quite good. If you're calcium deficient, which almost everyone needs more, it's one of the big four, cal nitrate, even at 2 kilos per hectare, which is $1 or $1.20, I think now, with some fulvic acid, will give you a calcium fulvate, which is really well uptaken. You might put some boron with that, for example, and have the two important calcium and boron together. So yeah, that's the kind of things that we're talking about. And of course, the biggest thing in foliar and the biggest understanding in broadacre is to understand the importance of urea as a foliar spray. Many people have not wrapped their heads around how and why it's so important, and why so many people are having so many good results across the globe with switching to, in some cases completely, to using urea as their primary nitrogen source as a foliar. Now, just really briefly explain, and hopefully you wrap your head around it. I mean, so you've got nitrate, nitrogen, ammonium, nitrogen. You've got a third source of nitrogen called the amine form of nitrogen, which is urea. And urea, of course, is a natural compound. It's just that organic people don't like the use of urea because it wasn't harvested naturally, but it's exactly the same nitrogen that's found in urine, which is the highest natural nitrogen, not animal poo. Animal urine is what contains all the urea. So when you take the amine and put it in the soil, an enzyme called the urease enzyme kicks in immediately. So you put urea in the soil as urine or as 46% urea. And in quite a short period, you've converted that amine form through to ammonium nitrogen. And ammonium nitrogen's got a single charge that sits on the clay collar with its light grip. And if there's a bit of warmth and moisture, a bunch of organisms called nitrifying bacteria come woofing in and they convert the ammonium to nitrate. And nitrate, if you've used too much urea, that's a downside because nitrate goes in with water and you've got too much, the plant doesn't differentiate, it just sucks it all in with a lot more water and you've diluted everything and created a calling card for insects effectively. But when you've got the nitrate in the leaf, it's a hugely energy intensive process to switch that involves molybdenum actually, and an enzyme called the nitrate reductase enzyme to convert nitrates through to the first stage of protein. Then it's real easy. The two next stages, the three steps to a protein. The first is taking a nitrate and converting it to the amine form. Wait a minute, that's what urea started life as. And then amine just goes click amino acid, click protein. It is so efficient without any, when I say sucking energy, there's suggestions that it's up to 17 to 19% of the plant's energy just to convert the nitrate through to the amine. Well, that's 17 to 90% less than your bank account, you could argue reasonably convincingly, because you suck the energy that could have gone into yield. So when you foliar spray urea, and foliar spray, I understand, is 12 times more efficient than putting it in the soil, you've taken the amine, you bypassed all that whole step of converting it to an ammonium, and then to nitrates, and then flooding the plant potentially with water, and then sucking all that energy to get it back to where it started. Why not bypass that and foliar spray the amine straight on the leaf 12 times more efficiently, click amino acid, click protein, no off-gassing, no leaching. You put humic acid with it, which complexes it and forms a urea humate. It is just a no-brainer. Everyone that's doing it absolutely loves the outcome. It's urea as a foliar. Of course, you can't do it if you're organically certified, but there's nothing wrong with it. You can measure Brix levels before and after and see increases in Brix levels. You can measure soil life before and after a foliar urea and watch the increase because you've greened up that plant with the most important mineral, the most abundant mineral for chlorophyll so quickly. And you've now got more sugar patches feeding more goodies to the organisms beneath them. So it's really hard. I mean, organics tars things has been some horrible thing, but I use one guideline: does nature approve of this? And nature does approve of foliar urea. There is no doubts about it. There's just no dispute. Okay.
Thank you. Rhonda has asked, how can triacontanol be used to improve photosynthetic activity?
Well, I've formulated this quite unwieldy range that we've developed over the years, and we've got quite a couple of exciting new things coming along the way. But of all the things I've used in formulation, and there's been a lot of them, triacontanol's got to be up there amongst the most important of them. It's a natural substance that was discovered in the late 80s from a fatty acid. No one ever thought that fatty acids had any potential as plant growth promotants, but fatty acid found in the lucerne plant. And if you take lucerne plantings that have been grown for seed and you've got bees there to pollinate them, the bees will build that fatty acid into their wax. And then there's quite a biochemical challenge to remove that from the wax, which we've done, and there's others that have done it as well. And it becomes this ridiculously inexpensive. Its mode of action is that it boosts every aspect of photosynthesis. It's like if you were to dream up the very best plant growth promotant, it wouldn't be gibberellic acid, which pumps the plant up, and you've got this leggy plant with twice as much organic matter but half as much nutrition by speeding cell division. No, the very best thing you could develop was something that boosted every aspect of photosynthesis, and that's what this thing does. Every aspect, like stomatal opening improves, your chlorophyll density improves in one study by 35%. You've got phosphate-based enzymes that drive the production of sugar. Their activity improves. There's more uptake of CO2. The list just goes on. It's like everything to do with photosynthesis affects, and its costs in broadacre scenarios, by and large, it contains a couple of dollars a hectare. And you can even, as on the podcast, I teach people how they can even make it themselves. It's just that you haven't got control of how much you're using. You can use this BAM or EM to ferment, and the lactic acid produced by those organisms can dissolve triacontanol, and you can make your own, but you sort of don't know what you got in there. Usually people dilute it at 1 to 50 and sort of, it's a bit of a spray and pray, but it does work. I mean, you can go and check say, rose growers in the US who wax lyrical online about all the awards they've won with this wonderful thing called alfalfa tea, and they don't know what they're actually doing. They're fermenting the alfalfa, and they think it's the lucerne, but of course it's the tricontinol that they're dissolving and haven't realised that. But it's won them lots of prizes. It is really special, really special. If you've not tried tricontinol, you need to go and try it.
Thank you. In a multi-species pasture or cover crop, what recommendations do you have around leaf sap testing to check nutrition status of the pasture as a whole? Do you also have comments about the relative merits of tissue and sap testing?
Okay, so the tissue testing is difficult in a multi-species cover crop because there's different guidelines with standard dry leaf analysis. So the two techniques are, of course, you're extracting sap and you're measuring the sap, which is relatively new. It's, you know, a decade in the making. And the older technique, which is 50 years in the making and 50 years of science behind it, is ashing the leaf and then analysing the ash with the same machine that's used globally. There's no variation in the readings, not like soil tests where there are different extracts used by different labs. The readings mean the same everywhere. And there's been guidelines for different stages of different crops and lots of research done on where you should be at various stages of tillering or wherever you are with wheat. And so I tend to favour, but they've both got roles to play. I tend to favour the dry leaf just because it's got more science behind it. But the sap has got some other gains in the sense that part of the sap model and the emergent sap model, and it was started by a friend of mine in Holland, is the concept of doing top leaf, bottom leaf. And so there, I suggested it and he went ahead and did it. But you know, there are 4 minerals specifically that are super mobile, and conventional dry leaf testing is simply not reliable, particularly for the most important, or arguably what I call the money mineral, which is potassium, because potassium has plays such a role in yield. But potassium is the most mobile of all minerals. And the moment there's a potassium shortage, it vacates the lower leaves and slowly moves up and sucks from the plant. And you're measuring the first fully developed leaf, you're measuring where it's moved to. And by the time you finally figure out with that leaf that you've got a potassium deficiency, you might have had it for a month and you'll never catch up. You'll make up some of the lost ground, but you lost yield every time when that happens. So a potassium meter is really handy in the field. You just do top leaf, bottom leaf. They've got to be the same. If there's 10% lower on the bottom leaf, you need to come in with a foliar or something of potassium during the season. But the sap test does that. You do top and bottom. There's only one lab, I can't remember what they call the Tasmanian lab, that's doing that top leaf, bottom leaf test. But it is good, and it's a valuable add-on. I'm thinking about introducing it and having both off there for people. Now that there's a lab in Australia doing it. It was a real problem sending it off to Holland and so forth because of, you know, from where we are in the world and so forth, to send living plants and little eskies to try and keep the sap intact and so forth was a bit difficult. So back to the cover crop question about, you know, how do you test? Well, you can't just mix them together. The idea of you know, going out into a pasture and grabbing some clover and some ryegrass and whatever else and just mixing them all together and sending it in, although the rural stores will tell you that's acceptable, it's not. If you look at the guidelines, particularly with dry leaf analysis for those, they're quite different. They've got different requirements. I mean, I guess it can give you a very, very vague idea of what's happening, but you're far better off to just take a clover or just take ryegrass or take whatever it is in the cover crop, blend some canola or whatever you might have in your cover crop, and just test that. And then you've got the guidelines relative to that will be much more specific than just bunching them all together and sending it off.
Does that answer your question? Is it Robert? And Rhonda, feel free to jump in if you have more questions around tricontinol as well.
Yep. So what you're saying, Graeme, is go select a species out of your multi-species mix, and probably one which has got some data behind it. So a cereal or a clover or a legume.
Exactly. That's what I would do in that scenario. And it's usually gives you a fairly good indication of what's happening.
Okay. Thank you.
Okay.
Thank you. Jessica, I think, is next. Jessica has a certified organic liquid potassium humate product that they're using, consisting of 10% humic acid and 5% fulvic acid. She understands that fulvic acid is used as a chelator and a buffer. Would this product be effective to use for this purpose when adding other trace elements, etc.?
The only thing to be aware of is that that some of the humics, most of them, they're extracted with potassium hydroxide, and that one will be as well. They're allowable in organics now. But the problem is that you've got this very alkaline material in almost everything. Maybe not so in organics, but obviously sulfate based, which you can use in organics. Nitrates you can't, but sulfate based trace minerals that you might want to collate with that material, the humic, can very often fall out of suspension because it doesn't like it's alkaline, and you put it with something acidic, and sulfate-based trace minerals are acidic, and you create Vegemite in the bottom of your tank. So you'd want to jar test it first, because otherwise you're not going to have much of a smile on your face if you've got that dropout outcome that can often happen with the humic. And fulvic's fine. Fulvic's compatible with everything. Humic acid basically is compatible with urea and sodium borate as the only two things it goes with. So you might be better just using straight fulvic if you want to mix it with a variety of things.
Is that helpful, Jessica?
That's very helpful. Thank you very much.
No problems.
James, I think James is in New Zealand for context. James was asking about the biofert. He's also asked, can you use fulvic acid with your foliar N rather than humic acid?
You can, but humic acid's cheaper, so that's why. If you want to put something else with your foliar N, it's a good question. If you're going to put something else, like say you want to put some zinc or some boron with your foliar N, which might be the case, or any other trace mineral for that matter, fulvic acid allows you to do that, because fulvic goes with everything. Humic acid is really just with, I don't want to promote things, but we've got a new thing called Fulvex, which is half fulvic, half humic, and we've developed the humic acid that is compatible. It gets released next week. But anyway, I don't want to advertise, but that is possible. You can do it. So we've managed to do it. The benefit of having the humic and fulvic together is that they do quite different things, and fulvic can leach. In terms of stabilizing minerals that are very leachable, will only humic basically can grab hold of boron and form a boron humate, and that boron simply can't leach. Humic acid can't leach. It's 10 times larger than fulvic acid. Fulvic acid is more active because it's so small. It'll go into plants, it'll go in through the cell membrane faster. It'll do similar things to what humic does, but more rapidly and more profoundly. But it can leach, and it does, and so it can grab things, and it'll give you that initial little kick. But humic will hold them in sandy soils. Like I've got one of my farms is beach sand almost. Well, not quite, because I've built quite a bit of humus now, but it's only got a CEC of 4. And so humic acid, nothing goes out without humic acid. That's why it's actually my motivation for developing a humic that could go with everything, so that we can fertigate with humic rather than fulvic, because fulvic can leach and humic can't, and we can hold things in the sand better. That's the motivation.
I've just put up your slide, Graeme, on fulvic acid for anyone's benefit as well.
So the difference between humic, they do very similar things. Fulvic does it more dramatically. Fulvic is more powerful chelating agent than humic. Of course, it goes with everything. But it's got one other interesting little thing that humic doesn't do. It's got 2 or 3 other things, but one of them is, and it's not really explained, the literature's not there. There's studies that have demonstrated that it's happening. They call fulvic the second sun because in cloudy, overcast conditions, to photosynthesize, which is what drives plant growth and productivity, you've got to have sunlight. It's the most important of the 3 components that are required: water, sunlight, and CO2, but sunlight's probably the most important of the 3. And so everything grinds to a halt, of course, if you've got no sun. What they've discovered is you can foliar spray fulvic acid in those conditions, and it's huge in Europe now, and because they have whole winters full of that with it, particularly in greenhouse production if they haven't got grow lights. And so you can foliar spray and the plant, you can measure it with a Brix meter, and the plant kicks in and starts making sugars again, and they can't really explain how it's working, but it does work. So that's why they call fulvic the second sun. It's quite a fascinating little side effect. Fulvic largely stimulates bacteria because it's much smaller and they're much smaller, and humic acid's got much more complex carbohydrates, and it's a very, very good fungal feed. So it's a great tool to use if you're trying to boost your fungi to bacteria ratio and lift your fungal numbers. That's when you use humic.
Hopefully,
Graeme, sorry. Could I just ask what sort of rates that the fulvic spray is going on in Europe as a second son?
Well, basically, it depends on whether you're using liquids or powders. I prefer the powders because fully soluble powders, because you're not cutting water around the place. But you're using rates like 0.5 kilo per hectare of soluble powder. Now, the other interesting thing with fulvic, and I refer to it as the fulvic flush, and it was discovered in Holland, but it's spread all over now, is that using higher rates of soluble fulvic acid powder, in this case 3 kilos per hectare, which is much higher than the 6 times more than the normal 0.5 kilo that I mentioned. 6 kilos, so 3 kilos per hectare, you can actually detox chemicals. And so in Europe, you've got to have your tests if you want to go organic, and you're always going to have chemical residues if you farm conventionally. Then you've got to wait 2 years. This isn't in conversion. You haven't even gone into conversion. You've got to go 2 years where you're not getting extra premium. And then you've got to go into conversion for 3 years, in conversion for where you do get premium, so you don't mind, you get extra money for the compared to conventional. But that 2 years puts up a lot of people. So what they discovered, the Dutch discovered it, was that putting out this 3 kilos of fulvic acid, basically it's got this massive cation exchange capacity, the highest known cation exchange capacity of 1400, and it sucks chemicals into it like it just sucks them into that massive absorbency. And we're only talking parts per million or billion of these chemicals, but they're there, and they can often be compromising subsequent crops. And so then fulvic acid's the most powerful bacterial stimulant, and it's bacteria that biodegrade things like glyphosate, for example. Fungi don't do it; it's a bacterial role. And so they come in, and if you put fulvic acid with your glyphosate, for one thing, you kill a third more efficiently, because both fulvic and humic do the same thing. They increase the uptake through a phenomenon called cell sensitization, where the plant membrane becomes more permeable when you suck in between 30 and 34% more, and that's very well researched. So a lot of people if they're using glyphosate, they put fulvic acid with it. But the second benefit, and it may even be a bigger benefit, is that now it's still tied to, after it's done its job and killed more efficiently, is tied to the fulvic. The bacteria, the only things that can break down glyphosate, come in and fast track the breakdown. They come like bees to a honeypot, not chasing the glyphosate. They hate the stuff. They're chasing the most powerful bacterial food, fulvic acid. So that happens when you're doing the detox rather than just glyphosate. If anything is biodegradable, you fast track the biodegradation. And then what doesn't biodegrade, because fulvic leaches, it leaches. So at least your soil's clean and you can get your organic certifications, go somewhere else, I guess. But from that perspective, you don't have to wait 2 years. You can test 6 weeks after you can certify, and then go and do conversion. So that's just an interesting thing. It's called the fulvic flush.
Thanks, Graeme. Ian's left a comment around common practice with many of his farmers is to use 1 to 3 applications of 20 to 30 kilos per hectare of dissolved urea plus 1 to 2 Brix Fix plus micronutrients in 80 to 100 litres per hectare total mix. Okay. Thanks.
So Brix Fix is our finding that wonderful thing called triacontinol works synergistically, and there seems to be just this sum is greater than the whole is greater than the sum of the parts when you combine. So it's basically a very good kelp that we have this blend of 3 kelps called trikelp. Trikelp and fulvic acid and triacontinol together you just get this big. Well, they all do. They've all got their own benefits, but together there's just some synergy that happens. And when we discovered it it's actually on one of my farms. We then replicated and said, oh my goodness, this is crazy. So and Brix Fix is in our top 10 products now. We've got lots of products, and that's only quite a short-lived product because it works so well, because you get the synergistic effect with those 3 components.
Joe has asked, can microbes go with fulvic?
Yes, they can. They go basically. It's really interesting. Even with your urea foliar spray, people say, "Oh no, surely it's going to kill the microbes." At one point, there was a company called Rum. I don't want to blacklist them, but they had this worm product. They sold lots of thousands of litres of it, and it had 14% N. And I was always thinking, how the hell is that possible? There's nothing with 14% N. It's just not possible. There's nothing organic with 14% N. There just simply isn't. You can get concentrated amino powders and things, but not in liquid form like that. And so So I thought, well, for one thing, and I poured it. I bought some, and it works really well. And I poured it onto some worms, and they squirmed in an obvious discomfort. And I thought, well, that obviously didn't come out their back end if it has that impact on them. But what I was interested in was whether that vast diversity of organisms that you find in worm juice, which was the base of it, whether they existed in the presence of 14.2% nitrogen. So I sent off and got analysed, and they do. They didn't even worry them. So you can put microbes, brood microbes with your urea, no problem at all. They seem to quite like it, and particularly when you've got the humate buffering any potential burn or anything. So that bacteria specifically, which is predominantly what's in the worm juice, they love it. I mean, their body's 17% nitrogen. They go into hyperdrive and all that nitrogen. So yeah, you can put out microbes with your urea if you chose.
And Callum has asked, when chelating minerals with fulvic, is it more efficient to add citric acid to get the mix to the optimum pH?
So the citric acid concept is relative to one thing, and it's relative to using glyphosate. So there's one of the things we teach in the 5-day courses and on the short courses as well is the concept that all chemicals we now understand have a sweet spot, a pH at which they're most efficient, and it's really can be quite dramatic. If you look at the world's most widely used chemical, which is diethane, most widely used fungicide, not chemical, because glyphosate tops diethane, but diethane is the most widely used fungicide. And you look at the ideal pH for diethane. If you use diethane, which is mancozeb, at say pH 7, so it's just some bore water or some tank water with neutral pH 7, and that's what your tank water that you diluted it in. The half-life at pH 7 of diethane is 18 hours. So if you put it out, you get double the half-life. So you've got a day and a half basically for your $40 or whatever diethane costs per hectare. You've got a day and a half's protection against fungal disease. If you drop it, and that's where citric acid comes in, and citric acid becomes an essential tool in the shed because most of them work better in acidity, and you need a pH meter in a bag of citric acid. You drop the pH of diethane down to 5.2, the half-life becomes 18 days, which means the full life is more than a month. So now you understand, without being cynical, why it's not on the label, because one way you're going to buy a lot more diethane. One's a day and a half, one's a month, just by dropping the pH, and that's where the citric. Now with glyphosate, the finding is that it's the most acidic. It's a sweet spot is the most acidic of any chemical. It's 2.9. So citric acid, you could use anything to acidify. You could use vinegar, you could use phosphoric acid, sulfuric acid, but citric acid is a really good thing. It's cost effective, and citric acid is a chelating agent. So basically, the citric acid that lays round after you've combined it to lower the pH down to 2.9 for your glyphosate, you're going to form calcium citrate and magnesium citrate and so forth on the soil and increase the uptake of minerals. So you're doing 2 with 1 in that instance. So it's my favourite for an acidifying agent. But the rule of thumb with citric acid is 100 grams per 100 litres drops that pH from, say, 6 to 5. 1 pH point is 100 grams of citric acid per 100 litres of liquid. So if it's 7, you put 100 grams in, now you're 6. You put 200 grams, you're 5. 300 grams, you're 4. 400 grams, you're 3, and that's about where you need to be. So, and 300 grams is about $2 worth of citric acid. So, and you're saved immediately about a third. You can use a third less glyphosate at that sweet spot pH. So it's a net gain for the growers to understand that. Many people have done it. So if you put fulvic acid and citric acid, you've got a double hit. Many people have halved the amount. You usually start off with 30% less, but many people have halved the amount of glyphosate using that combination.
We've got one last question before we wrap up from Dougal. Urea, micronutrients, biology, how do they go with your common in-crop weed control herbicides?
The biggest thing to be aware of with the herbicide is that you don't want to be putting anything that say humic acid you would never put with glyphosate, for example. You would never use humic acid. Humic acid's got a pH of 11. So while you'd be increasing the uptake, because humic and fulvic both do that increased membrane permeability where you suck more in, but you're taking it with one hand and giving with the other, because now you've created an alkaline scenario where the chemical works less efficiently. So you've made it more efficient and less efficient, and you've got no net gain. So fulvic acid is the material you use in those scenarios. Sorry, what was the question? I digressed then and I lost the question. What was the question?
Well, how does urea, micronutrients, biology, how do they go with common in-crop weed control herbicides. Feel free to.
So the main thing, so the main issue with the herbicides is that you can use them, but you just got to be aware of that end pH for the herbicide. We can supply you with a list of 5 pages of the sweet spot for all the various chemicals, including herbicides. You don't want to, lift it above its sweet spot with the additives you put in there, depending on what those additives are. So as long as you're aware of that, and even if you adjust it with a little citric acid if you need to, then that can work fine, and many people do that. You can combine them all.
Is that helpful, Dougal?
Yeah, no, that's great. I was just trying to reduce the amount of passes we do with the sprayer.
Yeah,
so yeah,
you can do that definitely.
Awesome. Well, we finished on time. That's amazing. And Lane would love to see the recording. Yes, we'll be recording. And we'll send that out tomorrow alongside a survey. Thank you, Graeme.